Gravity anchors you to a world wrapped in air and water. Above the clouds, sunlight meets no resistance. Metal heats without breeze, shadows freeze, and Earth becomes a sphere turning through darkness. From space, nations disappear. You see only a planet orbiting a typical star. That star is one among hundreds of billions in the Milky Way, and the observable universe holds at least 2 trillion galaxies, continental islands of stars drifting through time. That single fact alters how we measure distance and imagine our place. Tonight we move outwards step by step. We will cross the scarred interstellar cavity around our sun, trace how stars form in spiral arms, and approach the black hole that binds our galaxy together. We will meet Andromeda, not as a guaranteed collision, but as a neighbor whose future with ours is debated. Will gravity merge us, send us past each other, or lock both galaxies in a long orbital dance? The universe rarely offers certainties, it offers motion. If you enjoy journeys that change how you see reality, please like and subscribe and tell us where in the world you are listening from. Let's begin. The first meters of ascent feel familiar. Wind, noise, vibration. Then the air weakens and the horizon bends. Mountains flatten into patterns of mineral and cloud. From orbit altitude, weather stops being an event and becomes a system. Lightning is not a threat, it is a symptom. Green auroras trace where solar wind grazes the magnetosphere. You are no longer walking the world, you're observing a moving boundary between gas and vacuum. Space begins not where air disappears, but where flight loses meaning. Above this height, thrust replaces lift. Oxygen becomes hardware. The planet still holds you in its gravity, but your senses begin to adjust to a universe where up and down are local ideas. Climb higher, and the atmosphere behaves less like air and more like layers of diminishing resistance. The troposphere, the realm of storms and weather, is dense and turbulent. Commercial airliners ride near its ceiling, using the stability of thinner air to move faster. Beyond this band lies the stratosphere, where ozone absorbs ultraviolet radiation and scatters sunlight into soft gradients of blue and gold. Sound carries poorly here. Jet engines roar in the cabin, but their exhaust disappears into silence outside the skin of the craft. Heat leaves slowly because molecules are too sparse to carry it away. Human bodies evolved to breathe and radiate through air. Above the stratosphere, both become compromised. By 30 kilometers, the curvature of Earth is unmistakable. The planet is no longer a floor beneath you, but a horizon rising on all sides. The sky darkens not because night has fallen, but because it has thinned. Sunlight pours through uninterrupted, turning metal surfaces blinding white. Pilots speak of seeing stars at noon, shimmering faintly through the thinning blue. Propellers and wings are useless, only momentum and pressure gradients still matter. Survival equipment replaces comfort. Your lungs would fail without it. Astronauts describe the moment of crossing into orbital flight, not as liberation, but as inversion. You do not go up. You fall sideways with enough speed that Earth curves away beneath you. Space is reached at roughly 100 kilometers, the Kármán line, but that number is a convenience. It is not a wall. It is simply where aerodynamic lift becomes insufficient to counter gravity. The transition is gradual. At 80 kilometers, the air is as thin as the surface of Mars. At 120, atmospheric drag becomes intermittent bursts of ionized plasma. The boundary is not a switch. It is a fading memory of flight. Viewed from orbit, Earth is a living engine. Oceans spiral in gyres tens of thousands of kilometers wide. Jet streams circulate in bands, shaping continents with drought and rain. Thunderstorms bloom like cells, expanding and collapsing in minutes. Landforms are no longer borders and nations, they are tectonic scars, mountain ranges thrown upward where plates collide, deserts where ancient seas evaporated. Seeing the planet this way does not diminish it. It reveals the scale of processes that remain invisible at ground level. Then comes the psychological shift. In low Earth orbit, the planet occupies half of your view. You feel near it, held by it, but also separate. Astronauts speak of the overview effect, not as poetry, but as a cognitive recalibration. The human brain evolved to see landscape in fragments. A valley, a coastline, a city. Orbit compresses everything into systems. You see that storms are not disasters, they are heat redistribution. You see that rivers are not borders, they are transport networks carved by gravity. You see that the thin blue arc of atmosphere, the membrane that permits life, could vanish in silence if solar wind were not deflected by Earth's magnetic field. The planet rotates beneath you, completing a revolution every 90 minutes. Night sweeps forward like a tide. Cities ignite in constellations of sodium and LED, clustering along coastlines and river mouths. Then sunrise arrives not as a gradual dawn, but as a blade of white fire, cutting the darkness at orbital speed. In seconds, shadows vanish. Temperature jumps, solar panels wake. The boundary between day and night is not a cycle. It is a line you cross repeatedly. You remain anchored to Earth in a way your senses struggle to reconcile. You are weightless, yet captured. Free, yet bound. The horizon is no longer a limit. It is the first lesson of spaceflight, that escape is not achieved by leaving gravity, but by learning to live within its reach. The upper atmosphere unravels its layers. Turbulence falls silent, color drains to indigo, then to black. Gas molecules rarely collide, drifting in long arcs. Sunlight no longer scatters blue, it punches straight through. Astronauts describe the view not as a window, but as a wall of black swallowing every direction away from Earth. The planet glows beneath, but space stays indifferent. In this thinning environment, there is no wind chill, no scent, no pressure. Heat escapes slowly, and sweat becomes useless. Here, the environment no longer shapes biology. Physics takes over, and survival becomes an engineering problem. In the stratosphere, the familiar logic of weather dissolves. Air currents stop climbing in great convective towers and settle into relatively calm sheets. Ozone absorbs ultraviolet radiation, warming pockets of this layer from above rather than below, a reversal of how heat behaves on the ground. Jet streams sharpen into linear rivers, shuttling energy around the planet. Beneath them, storms churn with fierce local drama. You understand why pilots refer to this region as a ceiling. Ascend further, and the mesosphere brings a new kind of quiet. This is where space dust burns, streaking neon trails across the night sky. The thin gas here cannot cushion friction. Meteors vaporize in flashes that last only fractions of a second. Humans cannot linger at these heights. Breathing pure oxygen is insufficient. Without pressurization, your own tissues begin to boil, not from heat, but because liquids evaporate freely when their vapor pressure surpasses ambient pressure. The risk is invisible, and it happens without warning. Every spacecraft that passes through this region must protect against a world that has forgotten how to hold air. At around 80 kilometers, the familiar sky becomes a plasma laboratory. Solar radiation tears electrons from atoms, leaving behind charged ions. Radio signals refract and bounce off these layers, curving across the continent instead of traveling straight. This ionosphere is why ancient transoceanic communications worked at all. It is less a part of the atmosphere and more a membrane, a boundary where the sun sculpts Earth's connection to the cosmos. During geomagnetic storms, this region crackles with energy, and the aurora becomes a brilliant wound stretched across polar skies. Food, biology, instinct, none of them matter here. Heat transfer is so inefficient that exposed metal glows under sunlight while shaded surfaces plunge toward freezing. Engineers call it radiative control. Human bodies evolved to cool through moisture and airflow, mechanisms that vanish once the sky thins enough. On Earth, sweat evaporates, carrying heat with it. At these heights, sweat simply pools. The air cannot carry it away. What keeps a person alive is not resilience, but systems. Regulators, pumps, valves, insulation, and schedules of maintenance. It is not space yet. but it is no longer Earth. Look downward, and you see storms blooming and collapsing like cells in a living organism. Hurricanes spiral, not as calamities, but as inevitable expressions of thermodynamics. Their eyes are not voids, they are regions where rising air has exhausted itself. Mountain ranges carve vortices in the winds. Rivers appear as threads of reflected light. Human cities, which seem large at ground level, shrink into delicate constellations of sodium and LED. Geography stops being personal. It becomes structural. Look upward, and the universe begins to reveal itself. The stars seem fixed, unmoving, but that stillness is an illusion of distance. Some of those points of light are hundreds of times the sun's mass. Others are small, red dwarfs barely capable of fusion. Their photons traveled years, sometimes millennia, before landing on your retinas. From the surface, you never truly see them. Air blurs and scatters their light. Here, their sharpness is startling, as if someone has cleared fog from a window that has existed your whole life. Astronauts often say the atmosphere is thinner than intuition allows. From the ground, it feels endless, a sky you could climb forever. From above, it is a fragile skin, more like the peel of an apple than a sea of air. You see why scientists worry about it, why solar storms matter, why greenhouse gases accumulate. The layer that separates oceans and forests from the vacuum is astonishingly small. And at the boundary, the last molecules drift. They no longer behave like a fluid. They travel in ballistic arcs, meeting almost nothing. There is no true edge, only a gradual surrender. The sky does not stop. It disperses until it becomes irrelevant. Past this point, wings are meaningless. Parachutes are dead weight. Everything that moves upward must rely on engines, mathematics, and the acceptance that nature's rules have changed. The atmosphere was the womb of life. Orbit begins with a paradox: constant falling, no descent. The spacecraft glides through atoms separated by kilometers of vacuum. Every orbit is a negotiation between inertia and gravity. Solar arrays warm as sunlight hits, radiators cool in shadow. Electronics endure radiation storms invisible to human eyes. Down below, the aurora curls like a ring around the poles, a record of solar particles crashing into the magnetic field. Crossing the exosphere is not leaving Earth. It is entering a relationship with momentum. The planet's pull follows you, subtle but permanent, tracing your trajectory with every second. The exosphere is the final thinning of atmosphere. Molecules here do not behave like gas. They drift in long ballistic arcs, sometimes circling Earth once before colliding with anything. Density is so low that friction becomes a statistical event, not a continuous force. Aerodynamic lift, central to aircraft, stops working. A wing cannot bite into nearly empty space, and a parachute cannot catch air that isn't there. What matters now is speed sideways, not upward. Orbit is achieved by falling around the planet faster than gravity can pull you down. At roughly 160-600 kilometers above the surface, satellites in low Earth orbit live within this transition zone. Their shapes are wide and flat, not because of aesthetics, but because solar arrays harvest light more efficiently than small reactors can produce power. The sunlight that warms them arrives without scattering. There is no haze to soften it. Surfaces facing the sun heat sharply. The shaded side cools rapidly. Thermal control is a daily engineering exercise, not a convenience. From here, Earth turns beneath you like a slow wheel. The boundary between night and day, the terminator, is thin and abrupt. Lightning crackles across storm systems on the dark side, while ocean clouds on the daylight side shimmer with reflected glare. Cities appear as branching lines of sodium yellow and white LED, outlining coastlines and river deltas. Maps lose meaning, patterns reveal themselves. Humanity clusters where trade, terrain, and water allow. Even at these altitudes, Earth's presence is absolute. Atomic oxygen, energetic and reactive, erodes exposed spacecraft coatings. Engineers account for this abrasion, the way sailors account for salt water. When the sun becomes active, the exosphere expands. Satellites feel increased drag and slowly spiral downward if uncorrected. A solar flare launched weeks ago can alter a spacecraft's path today. Nothing here is static. Weightlessness is not the absence of gravity. It is continuous acceleration shared by every object on board. A wrench and an astronaut fall together, so neither seems to fall at all. Push gently from a wall and you drift for minutes. Spill water and it forms spheres, held together by tension rather than gravity. Motion becomes intention made visible. Radiation is the unseen hazard. Charged particles from the sun and cosmic rays from outside the solar system strike electronics directly. A single particle can flip a memory bit, corrupting navigation or shutting down systems. Satellites carry shielding and redundancy to survive these impacts. Human physiology has no comparable defense. Exposure is measured, tracked, and minimized. Relativity matters here. Clocks on board satellites tick slightly differently from clocks on the surface. The difference is small, but GPS constellations would drift kilometers per day without correction. Time itself becomes an engineering parameter, not a philosophical idea. Beneath you, the aurora reveals the magnetosphere in action. From orbit, the display looks like a living boundary, waves rolling across the upper atmosphere. It marks where energy from the sun meets Earth's defenses and dissipates. Crossing the exosphere is not escape. It is entry into a regime where momentum is currency. Gravity has not relaxed its hold. It has simply stopped producing consequences like weight and friction. To remain here, you honor motion. To alter course, you spend fuel. Space begins where the atmosphere no longer carries you, and only velocity can. At orbital velocity, you do not hover. You escape the ground by missing it endlessly. Satellites occupy lanes that never meet. Low Earth orbit for observation, geosynchronous rings for communication, graveyard orbits for the dead machines that can no longer maneuver. Each altitude carries a different balance of drag, radiation, and collision risk. Weightlessness is not the absence of force, it is uniform acceleration. Every object around you is falling, together, in silence. Inside a spacecraft, movement becomes negotiation. On Earth, your body manages momentum without thought. In orbit, a fingertip on a handrail can send you drifting across a module. If you twist too quickly, you rotate slowly for tens of seconds. You do not stop unless you find something to hold. The lack of friction means posture and intent matter more than strength. Astronauts quickly abandon walking in favor of gentle hand-based locomotion, anchoring themselves with straps, loops, and Velcro pads. Fluids behave differently. Coffee does not pour. It clings to surfaces and forms floating spheres held together by surface tension. Tears do not fall. They remain attached to the eye until wiped away. Objects have no weight, but they still have mass. If you try to shove a storage container aside, the container will move, and so will you, drifting in opposite directions with equal momentum. Gravity still acts on every molecule of your body. But because everything accelerates uniformly, you feel no force. Outside the station, orbital space is organized by energy. Spacecraft in low Earth orbit lose altitude over time and require periodic reboosts. The International Space Station, for example, continually adjusts its orbit to counter this decay. These maneuvers are modest, short burns, careful corrections, but they anchor the station's long-term stability. Higher orbits offer different compromises. Navigation satellites occupy medium Earth orbit because their altitude allows multiple receivers on the surface to triangulate signals with minimal atmospheric interference. Their operational environment is stable, but radiation increases. The Van Allen belts, regions where charged particles spiral along magnetic field lines, are strongest here. Engineers harden electronics, shield batteries, and plan maintenance cycles to keep systems reliable over years. Geosynchronous orbit lies much farther out. At roughly 36,000 kilometers above Earth, spacecraft circle once every 24 hours. To a ground antenna, they appear fixed in the sky. Weather tracking, international broadcasting, and long-range communications depend on this stillness. These satellites are large, power-heavy machines designed to endure decades of exposure to radiation and thermal extremes. When their fuel reserves run low, operators push them into disposal orbits to prevent interference with the corridor below. Space is not empty of hardware. A lost bolt or fragmented panel can strike with destructive energy. Agencies track debris constantly, issuing small course corrections when risk rises. These maneuvers are measured in centimeters per second, not dramatic rocket burns. The danger is mundane, cumulative, and predictable. Physical objects traveling at orbital speeds behave like projectiles. Human biology adapts, but slowly. With body fluids shifted upward, faces appear fuller and sinuses congested. Bones unload and begin to lose density. Muscles weaken without resistance. Astronauts counter this with exercise, not preference. Hard vacuum, radiation, and the absence of gravity are indifferent to comfort or habit. The routines exist because physics demands them. Freefall reshapes how the planet is seen. From inside a spacecraft window, continents do not announce borders. They present coastlines, drainage basins, and tectonic scars. Weather systems swirl across oceans without regard for cities. The perspective is not philosophical, it is physical. Orbital highways exist because Earth's gravity and rotation define stable paths. To remain here is to work with those paths, not against them. You are not defying gravity. You are traveling within its geometry. Approach the moon and light becomes sharp. Without atmosphere, sunlight strikes unfiltered, painting shadows so black they look carved. Dust rises and clings because electrostatic charges outcompete gravity. The soil remembers every impact, nothing erodes its scars. Move here and your stride becomes long arcs. Each jump lasts longer than instinct predicts. The horizon curves tightly, reminding you how small this world is. The moon was humanity's first step into cosmic space, not because of distance, but because it showed us how motion changes when air disappears. The difference begins the moment you slow into orbit. Earth's atmosphere blurs edges with haze. The moon offers no such mercy. Crater rims outline themselves cleanly, and the dividing line between day and night, the lunar terminator, sweeps forward like an advancing blade. Sunlit terrain is stark and blinding, while adjacent areas dissolve into the total darkness of shadow. A rock half a meter away can vanish completely. Human eyes evolved to see through filtered light, not the raw solar spectrum on bare regolith. Landing is a negotiation with dust. The surface layer, crushed by billions of years of impacts into microscopic shards, is abrasive and persistent. Engines stir it into clouds that do not billow. They rise and fall like slow curtains, influenced only by momentum and electrostatic charge. Where an atmosphere would diffuse debris, the vacuum preserves it. Astronauts from Apollo watched plumes of dust travel in clean parabolic arcs, falling exactly where physics predicted. No turbulence, no diffusion, no breeze to carry particles elsewhere. Gravity defines motion differently here. At 1/6 of Earth's pull, effort propels you farther than expected. Walking becomes a series of hopping steps, not because astronauts were seeking novelty, but because their center of mass traveled too far with every stride. Equipment responds with equal exaggeration. A dropped tool does not thud into soil, it falls gently, tracing its path for seconds. The moon teaches that gravity is not binary. It is a spectrum, shaping movement with the same consistency on a crater's edge as in the void above it. Temperature swings create another reality. Without air to buffer heat, surface rock bakes under sunlight, then freezes during lunar night. The difference is extreme. Hot enough to warp exposed metal during the day, cold enough to make steel brittle at night. Spacesuits are not garments here. They are circulating systems of pumps, insulation, and thermal plates, regulating heat through controlled radiation. Skin cannot cool itself by sweat. Respiration cannot vent warmth through convection. Survival depends on engineering, not reflex. The moon's silence is absolute. There is no sound transmission through vacuum. Hammering a probe into the soil produces vibrations you feel through gloves and suit, but nothing reaches your ears. Communication becomes radio waves, not voices carried through air. Even footsteps are visual events, dust rising and settling, rather than auditory cues. This sensory deficit is not eerie. It is simply the absence of a medium. Look outward, and space becomes immediate. Stars do not twinkle. They burn in steady points, unaffected by atmospheric scattering. Earth hangs above the horizon, a luminous disk occupying the sky with size and color no photograph conveys. Its blues, browns, and whites swirl motionlessly from this vantage. Planetary perspective reverses. Earth is the changing object, rotating through clouds and weather systems, while the moon beneath you stays fixed and unbending. The surface itself records history with perfect honesty. Each crater maps an impact. Large, shallow basins from ancient collisions, tiny pits from grains of interplanetary dust, where wind and water reshape Earth, the moon preserves. A footprint can last millions of years, not as myth, but as physical fact. The vacuum protects memory by offering nothing to erase it. Human tools behave differently here too. Batteries drain faster in cold shadow. Lubricants freeze. Dust infiltrates hinges and seals, grinding mechanisms with microscopic glass. Machines must be designed to endure an environment that never forgives contamination and never repairs damage. The moon is not hostile in the emotional sense. It is simply indifferent, a surface that reacts only to physics. Standing here, you understand why this place matters. The moon is not merely a symbol of exploration. It is the closest laboratory for understanding life without atmosphere, gravity at fractional strength, and sunlight unfiltered by air. It is where humanity first learned that stepping away from Earth means abandoning assumptions about motion, temperature, and sound. The moon did not challenge those ideas, it replaced them with new ones. Seen from lunar orbit, Earth hangs bright, wrapped in storms that move like continents of vapor. The moon and Earth share a barycenter, a common gravitational pivot buried beneath Earth's surface. Tides respond to this geometry, shaping shorelines and stabilizing climate. Lunar gravity keeps Earth's tilt steady, which allows seasons to repeat predictably. Without this partnership, long-term habitability might falter. The system is not decorative, it is a balancing act that enables life to persist over millions of years. The gravitational connection begins with momentum. The moon orbits Earth, but Earth also shifts slightly in response. Both bodies move around their shared center of mass. That pivot lies beneath Earth's crust, which means the planet constantly adjusts its orientation as the moon circles. These adjustments are subtle, but persistent. They keep Earth from tumbling chaotically, and they distribute rotational energy across ocean basins. Tides reveal the mechanism. The moon pulls more strongly on the side of Earth closest to it, and less strongly on the opposite side. The result is two tidal bulges, not one. Continents interrupt the water, forcing it to channel through bays and estuaries. Shorelines do not simply rise and fall. They respond with unique rhythms. In some locations, the range spans centimeters, in others, meters. This slow transfer of energy is friction against the spinning Earth. The planet loses rotational speed, and that energy is passed to the moon, pushing it outward a few centimeters per year. Laser reflectors placed on the lunar surface by Apollo missions confirm the drift. Each measurement shows the moon receding, millimeter by millimeter. Rewind that process billions of years and the moon appears much closer, dominating ancient skies and raising tides across continents not yet formed. The Earth-Moon system is not static. It evolves, and the pace of that evolution influences planetary conditions. Axial stability is the outcome most relevant to climate. Earth's tilt is roughly 23.5 degrees, and that tilt creates the seasons. With the Moon, variations in that tilt remain narrow. Without it, gravitational nudges from the Sun and other planets could drive swings of tens of degrees. Mars demonstrates this vulnerability. Its two small moons provide little stabilizing torque. Geological and simulated records indicate that Mars's tilt has shifted widely over time, altering ice caps and climate. Earth avoids those extremes because the Moon's mass anchors its orientation. The stabilizing effect extends beyond climate. Tidal forces move nutrients through shallow seas, affecting reproductive cycles in marine organisms. They erode coastal rock, carry sediment, and shape estuaries. These effects are not incidental. They have operated for hundreds of millions of years, establishing conditions in which life can adapt rather than endure abrupt upheaval. Even in deep time, evolution benefits from predictable cycles. The same gravitational partnership influences the solid Earth. Ocean loading, the pressure of water against continental shelves, applies steady stress to lithospheric plates. These stresses are small but constant. They do not cause earthquakes, yet they can affect when a stressed fault decides to slip. The relationship is not dramatic. It is incremental. Planetary environments change through accumulation, not single moments. In orbit, engineers rely on this consistency. Satellite trajectories must account for lunar gravity. Over months and years, the Moon's pull alters paths little by little. Spacecraft bound for deep space use lunar assistance deliberately, letting the Moon's mass shift their velocity without burning fuel. What seems like a quiet partnership at planetary scale becomes a navigational tool in engineering. Seen from the Moon, Earth's complexity is obvious. Oceans reflect sunlight as a single moving structure. Atmospheric bands stretch around the globe. Storms trace energy flows, not disasters. Vegetation darkens landmasses in seasonal waves. All of it rotates beneath a thin shell of air. In contrast, the Moon's surface shows no such cycles. No oceans to mix, no air to carry heat, no chemistry to erase the past. One world is dynamic, the other is inert. Their interaction is the difference. The Earth-Moon system is not an ornament in the night sky. It is a physical arrangement that moderates rotation, distributes energy, and preserves stability over geological time. The Moon is not merely nearby. It is engaged, shaping the space in which life can persist. Beyond Earth's shield, the Sun's particles arrive like a persistent storm. They travel at hundreds of kilometers per second, threading magnetic field lines. The magnetosphere forms a bow shock, slowing and rerouting this stream. Without it, our atmosphere would erode as Mars's did. Radiation here is not dramatic, it is cumulative. Sensors record counts per second. Solar flares spike unpredictably. Even spacecraft need shelter. Space is not safe or hostile. It is indifferent to biology. The Sun does not simply emit light. Its outer layers constantly shed ions and electrons, accelerated by magnetic turbulence in the corona. This solar wind expands outward in all directions, pushing against the planets. At Earth's distance, it has diluted considerably, yet it still delivers enough energy to disturb instruments and damage exposed tissue. The magnetosphere is our response to that flow, a cavity carved out of space by Earth's magnetic field. It is not a wall but a deformation, shaped by the solar wind's pressure on one side and our planetary magnetic dipole on the other. The bow shock is the first interaction point. Solar wind, rushing supersonically, meets the magnetosphere and slows abruptly, like air hitting the nose of a hypersonic aircraft. Downstream lies the magnetosheath, a turbulent region where the charged particles are redirected. They do not stop. They slide around Earth, guided by field lines toward the magnetotail, a long plume of distorted magnetic structure stretching millions of kilometers behind the planet. Space agencies monitor this region closely, because geomagnetic storms begin here. Energy occasionally penetrates deeper. When the interplanetary magnetic field aligns with Earth's, magnetic reconnection opens pathways into the inner magnetosphere. High-energy particles spiral inward and bombard the polar regions. Their collisions with oxygen and nitrogen produce auroras, green at lower altitudes, red and violet higher up. From the surface, the aurora looks like a display. From orbit, it is a luminous boundary, tracing the points where the magnetosphere absorbs excess energy so the rest of the planet does not have to. Radiation belts form on the night side of this environment. The Van Allen belts trap particles, locking them into circular orbits around Earth. They are not uniform rings. They compress and expand with solar activity, sometimes swelling enough to endanger satellites designed for lower exposure levels. Engineers route spacecraft trajectories to avoid prolonged transit through these belts. If they cannot avoid them, they add shielding and redundancy. The rules are practical, not emotional. Tolerances, thresholds, and dosages. The consequences of solar events propagate through every system we depend on. A strong flare can produce a coronal mass ejection, dense plasma hurled outward from the sun. If Earth happens to intercept the plume, electrical grids experience induced currents. In the upper atmosphere, heating increases density, raising drag on satellites. Spacecraft that normally glide through thin air encounter resistance, slowly losing altitude. Operators prepare for this by reserving fuel for orbital maintenance. There is no negotiation, only preparation. Mars illustrates the alternative. Its weak magnetic field cannot hold off the solar wind. Over billions of years, the ion stream stripped its atmosphere away, atom by atom, into interplanetary space. Mars did not lose its air in a catastrophic moment. It surrendered it gradually, unable to replenish what the wind carried off. Earth avoids that fate because its dynamo, the flow of molten iron in the core, produces a sustained magnetic field. As long as the core remains active, the shield remains functional. Spacecraft entering interplanetary space encounter the wind directly. Solar panels degrade under radiation exposure. Electronics accumulate damage each time a proton penetrates shielding. The deterioration is not obvious day to day, it grows over years. Missions succeed because engineers expect this attrition. Data is compressed, instruments are cycled, systems are duplicated. Spaceflight is less about conquest than accounting. Even astronauts rely on timing. Crews rarely perform extravehicular work when solar activity increases. They wait behind metal and polymer, not because danger is dramatic, but because dosage matters. Radiation does not announce itself. It accumulates in tissue, disturbs cells, and leaves effects long after the source has passed. The magnetosphere is not a barrier we built. It is a feature of a planet that still circulates heat within its core. Its value is not metaphorical. It is measurable in the air we keep, the oceans that do not boil away, and the technological systems that function without interruption. Beyond it, the solar wind continues, indifferent and constant. Closer to the sun, illumination becomes punishment. Mercury swings between furnace and cryogenic darkness. Venus hides beneath a crushing blanket of carbon dioxide, its atmosphere thick enough to warp metal and crush landers. Mars carries dried riverbeds, evidence that climate can change not in centuries, but in eons. The inner planets are cautionary records. Each reveals how star distance, atmosphere, and gravity write the histories of entire worlds. The sun dominates every environment here. Its radiation does not merely deliver heat, it shapes chemistry and motion. Mercury, the closest planet, rotates slowly while orbiting rapidly. Days there last longer than its year, making surface temperatures swing from over 400 degrees Celsius to far below freezing. Without an atmosphere to equalize heat, its terrain is carved only by impacts and solar weathering. Rock expands, fractures, and contracts without erosion to smooth it. Mercury is a planet defined by exposure, a body too small to retain air, too close to avoid extremes. Venus offers the opposite lesson. Roughly Earth's size, yet shaped by a runaway greenhouse effect, its atmosphere traps heat with relentless efficiency. Thick clouds of sulfuric acid reflect most sunlight outward, but infrared radiation cannot escape. The surface remains hot enough to melt lead, and the pressure at ground level exceeds that of Earth's ocean depths. Landers survive minutes before electronics and structure fail. Wind patterns move slowly near the surface, yet whip at hurricane speeds higher up, forming a global conveyor of dense gases. Venus proves that composition matters as much as distance. A world can be similar in size to Earth, yet uninhabitable due to feedback processes that amplify heat beyond recovery. Mars sits near the threshold. Its ancient valleys and delta fans suggest liquid water once flowed across its surface, perhaps under a thicker atmosphere. Today, the air is too thin to hold heat or protect against radiation. Temperatures drop sharply after sunset, and dust lifts easily into the sky, forming storms that can wrap the entire planet. These storms are not violent in a terrestrial sense. Winds are weak, but their fine particles are abundant and persistent, limiting visibility and cloaking solar panels. The contrast between Martian past and present underscores how atmospheric loss changes everything. Like Mercury, Mars lacks a strong magnetic field. Solar wind stripped its gases away over time. Orbital mechanics explain why these three worlds form a distinct category. Their orbits keep them close to the Sun, where heat, ultraviolet radiation, and tidal interactions are strongest. Planet formation models show that the inner solar system favored rocky material, metals, and silicates, while volatile compounds condensed farther out. Thus, the terrestrial planets all began with stone, not ice. Their differences emerged later, as atmospheres formed, lost, or transformed under solar influence. Gravity dictated retention. Larger bodies can hold gases, smaller ones cannot. Venus and Earth could trap molecules. Mercury, with weak gravity, could not. Mars kept some atmosphere temporarily, but not permanently. Instruments sent to these worlds reveal their past. Seismometers on Mars recorded internal tremors, indicating a cooling, contracting planet. Orbital probes around Mercury mapped chemical signatures of solar-driven surface changes. Venusian radar imaging pierced cloud cover, revealing tessellated highlands and volcanic plains. None of these findings deliver drama. They provide timelines. Each measurement tells how long processes took and how slow shifts accumulated into environmental collapse or stasis. Humans experience these differences indirectly. Materials engineered for Earth behave unpredictably on Mars due to dust, abrasion, and cold. Electronics fail on Venus within hours because heat overwhelms thermal protections. Mercury demands no aerodynamics at all. Descent requires pure thrust. Space exploration becomes a negotiation with conditions: which materials survive, which sensors endure, and which goals justify risk. The inner solar system is not a museum of failures. It is evidence. Each planet demonstrates that distance alone does not make a world safe, that atmospheres can preserve or destroy, and that gravity's role extends beyond pulling objects downward. It determines what a planet keeps and what it loses. Closer to the Sun, we see these truths exposed plainly, written into rock, temperature, and silence. Past the asteroid belt, gravity favors giants. Jupiter's storms roar deeper than oceans, fed by internal heat. Saturn balances rings with shepherd moons that sculpt them. These worlds stabilize the inner solar system by intercepting debris. Their mass defines orbital order. They are not failed stars. They are engines that shape the behavior of every smaller object nearby. Jupiter dominates the outer system the way the Sun dominates the inner. Its mass exceeds that of every other planet combined. The line between atmosphere and interior is not a surface, but a gradient. Hydrogen transitions from gas to liquid metallic form under pressure, conducting electricity and generating a powerful magnetic field. Lightning here stretches for hundreds of kilometers, producing bursts that would dwarf any terrestrial storm. The Great Red Spot, a cyclone larger than Earth, has persisted for centuries because no landmass interrupts its rotation. In a world without continents, weather is governed solely by temperature, chemistry, and momentum. Saturn's beauty is structural rather than decorative. Its rings are not solid. They are billions of fragments of ice and rock, organized by orbital resonances. Moons like Pan and Daphnis maintain clear lanes within the rings, pulling particles aside as they orbit. Gravity behaves like a librarian here, sorting debris by size and trajectory. The gaps and arcs in the rings do not mark absence, they reveal patterns of influence. Every moon is part of the system's governance, not merely an orbiting object. Uranus and Neptune extend the principle. They lack dramatic rings or sprawling storms quite as visible as Jupiter's, yet their influence is significant. These ice giants formed where volatile compounds condensed, accumulating methane, water, and ammonia. Their atmospheres appear calm from a distance, but their winds are among the fastest anywhere measured in the solar system. Neptune's jet streams reach speeds that defy Earthbound intuition. The gas flows freely because there are no mountains, forests, or continents to resist it. Gravity compresses, rotation accelerates, and energy moves along uninterrupted paths. The gas giants are not passive anchors, they act as filters. Over billions of years, their gravitational cross-sections captured countless comets and asteroids that might otherwise have struck the terrestrial planets. Jupiter, especially, acts as a sink for chaotic trajectories. Objects entering the inner system often encounter its influence first. Some are redirected into stable orbits, others are ejected entirely. Many fall inward and collide with the planet, leaving fleeting scars of heated gas. Instruments once watched a comet break apart under Jupiter's tidal forces before plunging into the atmosphere. The event lasted days, but the principle it demonstrated has been at work since planets first formed. Their gravitational influence also stabilizes planetary spacing. Orbital resonances, patterns in which objects complete whole numbers of revolutions relative to each other, keep moons, asteroids, and small bodies from drifting into chaotic motion. The asteroid belt itself is carved by Jupiter's pull. Regions of instability correspond to simple ratios of orbital periods, where resonant tugging eventually clears debris. What remains becomes either families of stable orbits or gaps where material cannot persist. Exploring these giants demands caution. There is no surface to land on. Descent becomes compression and heat until the probe fails. Spacecraft investigate by orbiting at distance or executing flybys, reading magnetic fields, sampling radiation, and mapping atmospheric chemistry. The hazards are not cinematic, they are environmental. Jupiter's radiation belts can disable electronics. Saturn's rings contain shards traveling at kilometers per second. Neptune's distance makes communication slow and power limited. Each challenge arises from physical environment, not narrative tension. Humanity uses the giants as stepping stones. Missions departing Earth often perform gravity assists, stealing orbital momentum from these planets. A spacecraft that swings behind Jupiter gains speed without burning fuel, trading tiny fractions of the planet's energy for enormous changes in its own trajectory. This exchange is precise and predictable, governed by the same laws that shape tides and seasons. The giants are not simply destinations, they are tools that make deeper exploration possible. Beyond them, the solar system changes character. Heat fades, sunlight weakens, and ice becomes structural. But the logic remains. Mass organizes motion. The gas giants are reminders that order in space is not chosen. It is enforced by gravity, expressed through storms, rings, and trajectories that endure for millions of years. Look closely, and rings are not sheets but swarms. Shards of ice and rock tracing lanes enforced by resonance. Moons fracture, collide, and reassemble under tidal stress. Some hide global oceans beneath ice, others erupt with geysers that coat neighboring rings. Gravity here is precise. It divides debris into families of orbits, each responding to unseen mathematical rhythms. Most ring systems begin with disruption. When a moon drifts too close to its planet, it can cross the Roche limit, the distance inside which tidal forces overpower its own gravity. Rock and ice crack, then separate into fragments that continue orbiting. Over time, these fragments collide, grind down, and settle into thin, flattened structures. From far away, the result looks like a solid disk. Up close, it is thousands of kilometers of individual particles. Saturn's rings show this architecture best. They are mostly water ice, ranging from dust grains to boulders. Small moons orbit just inside or outside key ring edges. Their gravity nudges particles into or out of particular paths, clearing gaps and maintaining sharp boundaries. These shepherd moons enforce order. When their orbits resonate with ring particles, say, 2 moon orbits for every 3 particle orbits. Repeated tugs carve lanes where material cannot remain stable. Jupiter's rings are faint and dust-dominated. Micrometeoroids strike its inner moons, ejecting tiny particles that spread outward. Radiation and sunlight slowly push the dust, while gravity keeps it confined. The structure is less dramatic than Saturn's, but the process is the same. Impacts supply material. Forces sort it. Uranus and Neptune add another variation, with narrow, dark rings held together by small, unseen moonlets. Moons and rings interact continuously. Tidal forces flex the interiors of some moons, converting orbital energy into heat. Enceladus, a moon of Saturn, vents water vapor and ice grains from fractures near its south pole. That material escapes and feeds Saturn's E-ring. Europa, around Jupiter, shows a cracked surface pattern consistent with an internal ocean warmed by similar tidal heating. These are not speculative stories. They follow directly from measurements of gravity fields, surface temperatures, and plume composition. Cratering records link moons back to ring formation. Some small moons appear to be reassembled rubble piles, their irregular shapes suggesting they are leftovers from earlier disruptions. Others show smooth regions resurfaced by internal activity or by gradual deposition from rings. No atmosphere smooths these features. Without wind or rain, every process is either impact, tectonic motion, or deposition from orbiting material. The orbital patterns themselves remain stable because of resonance. When 2 bodies complete orbits in simple ratios, like 1:2 or 2:3, their gravitational pulls repeat at the same points. Over long periods, this repetition locks orbits into configuration or clears regions entirely. Gaps, such as Saturn's Cassini division, exist where resonances make particle survival unlikely. The ring system becomes a visible map of which orbits are permitted and which are unstable. Spacecraft must treat rings and moons as active systems, not static backdrops. Passing through a ring plane requires choosing paths where particle density is lowest and where known moon orbits do not intersect the trajectory. Missions like Cassini used gravity from moons to adjust speed and angle, saving fuel while exploring different ring regions. Navigation plans are built on the same orbital mechanics that shaped the rings in the first place. Rings and moons in the outer solar system are more than scenery. They are the visible outcome of impacts, tides, and resonances acting over immense timescales. By studying how debris arranges itself and how moons respond to tidal stress, we learn how gravity organizes matter into structured systems, not just here, but around planets orbiting other stars as well. Beyond Neptune, the Sun dims to a piercing star. The Kuiper belt forms a diaspora of dwarf planets and frozen fragments. Their orbits tilt and weave, guided by subtle gravitational harmonies. Pluto is no mistake. It is an example of a world formed where sunlight weakens and volatile chemistry freezes into geology. Here the solar system stops being familiar and begins to resemble the outskirts of other stars. The Kuiper belt is not a line, but a region tens of astronomical units deep. It contains objects left over from the solar system's formation, bodies that never grew large enough to become planets, shaped instead by small collisions and distant gravitational nudges. The vacuum here is colder than the lunar night. Surface ices are mixtures of methane, nitrogen, ammonia, and water, frozen so solid that mountains and cliffs can form from chemistry that near the Sun would remain invisible as gas. Kuiper objects shine faintly, reflecting the Sun's weak light as they drift slowly along eccentric orbits. Pluto is our first detailed case study. Its surface displays fractures, nitrogen ice plains, and mountains of water ice harder than granite at these temperatures. A heart-shaped basin known as Sputnik Planitia demonstrates atmospheric transport in slow motion. Nitrogen vapor sublimates in sunlight, migrates across the world, and condenses elsewhere. Winds carry grains of ice across the plains. None of this behavior requires oceans or oxygen. just the interaction between cold chemistry, low gravity, and sunlight reduced to a distant glimmer. The New Horizons spacecraft did not discover a barren relic. It found active geology in a domain where energy is scarce. Beyond Pluto are objects even stranger: Eris, Haumea, Makemake, and thousands of smaller fragments occupy inclined and elongated paths. Their irregular orbits reflect a history of gravitational shuffling. Neptune, during the solar system's early evolution, migrated outward. As it did, its resonances swept through the primordial disk, capturing some objects and scattering others. The effects still linger. Bodies locked in a 3-to-2 resonance. Plutinos complete 2 orbits for every 3 of Neptune's. They do not collide because resonance sets a schedule. Repeated encounters at the same point cancel out rather than accumulate. Closer to the belt's outer edge, distances stretch into tens of billions of kilometers. Time becomes slow. Even the heat from the sun is negligible. Cosmic microwave background radiation begins to rival solar influence. In this environment, chemistry does not change quickly. Colors on Kuiper objects arise from the long-term processing of surface ices by ultraviolet light and cosmic rays, forming organic compounds called tholins. Over millennia, they darken and redden the terrain. Landscapes evolve not through weather or tectonics, but through gradual irradiation. Navigation through the Kuiper belt is not like crossing the asteroid belt. Spacecraft do not dodge swarms. Objects are widely spaced, separated by millions of kilometers. The difficulty lies in prediction. Most bodies are too small and faint to track continuously. They reveal themselves only when sunlight glances off their surfaces at the right angle. Mission planners rely on statistical maps, not catalogues, because completeness is impossible. Even with modern surveys, the known population is a fraction of what exists. The Kuiper belt marks a transition in structure. Inside Neptune's orbit, the planets dominate. Gravity arranges paths, clears regions, and enforces order. Out here, the sun's influence weakens, and gravity distributes matter without finishing the task. The result resembles the debris disks found around young stars: scattered clumps, tilted rings, and bodies that orbit on paths influenced by events long past. Our solar system once looked like this everywhere. The inner worlds we know are the survivors of collisions, mergers, and migrations. The Kuiper belt is what remained untouched. The frontier has scientific value. Comets that visit the inner solar system often originate here, perturbed by Neptune or by passing stars. Their compositions preserve the starting conditions of planet formation. Study a comet's ice, and you measure ancient chemistry. Track its orbit, and you infer the architecture of a region we can barely see. The Kuiper belt is therefore not an afterthought. It is a record, slow, cold, and durable. Beyond it, the sun's gravity fades further, giving way to a sphere of distant objects. The edge of the Kuiper belt is not the end of the solar system. It is the beginning of the domain, where everything moves by inertia and memory, influenced only gently by the star that once shaped it. Farther still, the solar system becomes spherical. Debris ejected during planet formation lingers in the Oort cloud, perhaps a light-year wide. Comets sleep here until a passing star or galactic tide nudges them inward. We cannot see this shell directly. Its existence is inferred from the paths of visitors. It marks the true edge of the sun's gravitational influence. Not a hard boundary, but a fading hold. The Oort cloud is a population of remnants that never became worlds. In the early solar system, as giant planets migrated, they scattered countless icy fragments outward. Some were expelled completely, becoming interstellar objects. Others slowed just enough to remain gravitationally bound, caught in vast orbits that no human lifetime could witness. Their distances are so extreme that sunlight arrives diluted to a barely measurable glow. On Earth, we call this region space. Out here, space becomes scale, millions of kilometers between one object and the next, with no horizon to anchor direction. We know the cloud exists because of comets that appear from trajectories no planetary disk can produce. Short-period comets come from the Kuiper belt and return frequently. Long-period comets arrive from all directions, taking thousands or millions of years to complete a single orbit. Their paths trace ellipses so elongated that perihelion brushes past the inner worlds, while aphelion vanishes into distances closer to neighboring stars than to the Sun. Only a spherical, distant reservoir can explain such geometry. Conditions here are not hostile or gentle, they are nearly absent. Temperature approaches 3 Kelvin, molecules barely move. Ice becomes as strong as stone, preserving the chemistry of the early solar system. These objects evolve not through erosion or atmosphere, but through radiation. Cosmic rays strike their surfaces for eons, darkening outer layers into organic crusts. Beneath that shell, original volatiles remain trapped, unchanged since the era when planets began to form. Every inbound comet is therefore a sample of unprocessed material, not a fragment weathered by tides or sunlight. Occasionally, a disturbance reaches this quiet sphere. A passing star shifts the balance of gravity. A giant molecular cloud brushes the region. Even the slow drift of the solar system through the Milky Way produces tidal forces that tug subtly on outer orbits. These influences do not sweep comets inward in waves. They alter trajectories one by one. A fragment once stable may acquire a fractional change in velocity, enough to tilt its orbit toward the Sun. The journey inward begins silently, unfolding over millennia. As the comet descends, sunlight strengthens. Surface ice warms and sublimates. Jets erupt from vents, creating tails that reveal its path. This transformation is not the comet awakening. It is physics, solar energy forcing vaporization where depths of cold once protected solids. The coma that surrounds a comet is not atmosphere. It is temporary and unconfined. Gas drifts away until solar wind pushes it into a visible tail. Every pass erodes the nucleus slightly. Repeated returns shrink these bodies, sometimes fragmenting them entirely. The Oort cloud itself remains unseen because it is too diffuse to detect directly. No telescope can map it as a structure. Instead, it exists in models derived from orbital statistics, population estimates, and dynamical simulations. Its size is described not as a number, but as a probability field. Within a certain radius, the Sun's gravity outweighs influence from the galaxy. Beyond that, external forces dominate. The transition is gradual, defined by the paths of bodies rather than an invisible border. For spacecraft, the Oort realm is inaccessible. Travel time would exceed human lifespans, propulsion budgets, and communications windows. Instead, we study what the cloud sends inward. Each long-period comet is evidence, a vector pointing back to a region that cannot be observed directly. Their trajectories chart the boundary's curvature, showing where solar authority weakens. The Oort cloud is not a frontier we visit. It is a reminder that the solar system is more than the planets we see. It stretches outward until gravity itself loses definition, blending into the influence of the galaxy. Here, the Sun is not a dominant presence, but one star among many, holding only what distance allows it to keep. Leave the Sun's domain, and space thins to almost perfect vacuum. There is no upwind or downwind, only motion relative to stars. Dust grains travel at lethal speeds. Radiation accumulates, like weathering. Navigation becomes probabilistic, fuel is precious, and momentum defines your future. Out here, distances stop feeling large. They feel permanent. Interstellar space is not empty, only quiet. Atoms exist, but so sparsely that a cubic centimeter may contain a handful. A spacecraft crossing this environment no longer uses orbital mechanics around a single body. It must plan a trajectory in relation to gravity wells scattered across light years. Small forces matter. The heat from onboard electronics, a misaligned thruster, or an uncorrected micro-impact can accumulate into coarse drift that becomes impossible to correct without fuel. Motion becomes accounting. Every change is a subtraction from a limited reserve. Radiation is constant. Without the magnetosphere's shield, High-energy particles from supernova remnants and ancient explosions drift freely. They do not arrive dramatically. They arrive continuously, embedding themselves in electronics and occasionally in human tissue. A spacecraft can endure for years if its components are hardened and redundant. Human bodies cannot. Shielding becomes mass, and mass becomes cost. Crews must hide behind water tanks or propulsion systems, using hardware not because it is designed for comfort, but because it is dense enough to absorb energy. Interstellar dust is more dangerous than interstellar gas. A particle the size of a grain of sand, encountered at tens of kilometers per second, delivers more kinetic energy than a rifle round. Spacecraft hulls must be layered or angled so that impacts disperse rather than puncture. Mission planners choose orientations deliberately, presenting the most protective geometry toward the direction of travel. Dust is not avoided, it is statistically managed. Communication becomes delay. A signal still moves at the speed of light, but the gulf between origin and receiver stretches the response into minutes, hours, or days. Guidance systems must act autonomously because no command can arrive fast enough to respond to emergencies. The idea of remote control ends at planetary scales. Beyond that, spacecraft become partners rather than tools. Machines entrusted to solve their own problems using onboard logic. Heat dissipation changes as well. In vacuum, conduction, and convection are absent. Radiators operate not by pushing heat into air, but by emitting infrared directly into space. They must remain cold enough to radiate efficiently, yet not so exposed that micrometeoroid strikes tear them apart. This is why deep space probes resemble open frames. Their surfaces are designed around thermal balance, not interior volume. Time loses the rhythm of orbits. In the solar system, distance is measured by transfer arcs and windows. Beyond it, motion is simply persistence. A probe leaves its star system, crosses the heliopause where solar wind weakens, and enters a region influenced by the galaxy itself. This transition is not dramatic. Density does not suddenly increase. Sensors record a shift in particle direction rather than amount. Cosmic rays grow slightly stronger. The sun becomes one light among many. The nearest star is more than 4 light-years away. Even at hypothetical high speeds, the travel time spans decades. Most missions aimed outward are not designed to arrive. They are designed to drift. Voyager and Pioneer continue not because they are still actively propelled, but because nothing slows them. Their trajectories describe patience, not urgency. The interstellar medium imposes no deadline. It only denies shortcuts. What matters here is that motion becomes identity. A spacecraft is defined by the velocity it carries when it leaves its last gravitational well. There are no aerobrakes, no fuel depots, no rescue options. Momentum is not merely useful, it is everything. Turn too sharply and fuel runs out. Turn too late and arrival becomes impossible. Exploration is measured not in destinations, but in how far the Voyager can preserve its speed. In this crossing, the universe stops feeling crowded. There are no nearby planets, no lanes of satellites, no orbits to reference. Only a vector, a slow rotation of stars around the horizon, and the long, silent interval between one gravitational influence and the next. Our solar system drifts within a cavity blasted by ancient supernovae. The local bubble is not empty. It is simply low density, its walls formed by denser gas clouds and star-forming regions. Cosmic rays penetrate easily here. These explosions occurred long before Earth formed, but their shockwaves still shape our interstellar environment. We exist inside the aftermath of stars that died millions of years before our own sun ignited. The bubble is not a sphere carved with intention. It is the result of repeated detonations from massive stars clustered near one another. Each supernova launched shockwaves through the surrounding gas, clearing it and heating what remained. Over time, these waves merged into an extended cavity. The interior is thin and warm, while the edges cool and condense, compressing matter into walls where future stars can form. We infer the shape not by seeing the void, but by measuring how starlight changes as it crosses regions of different density. Mapping the bubble relies on absorption. Dense gas absorbs certain wavelengths of light. Low-density regions do not. Stars behind the cavity appear brighter and less reddened than those behind thicker dust. By combining thousands of measurements, astronomers reconstructed the three-dimensional structure. An irregular volume, roughly 1,000 light-years across, bounded by clouds like Taurus, Perseus, and Orion. Our Sun is not centered inside it. We simply occupy a part of it during our orbit around the Milky Way. The bubble is not calm. Its interior retains heat because collisions between particles are rare. Where typical interstellar medium might contain a few dozen atoms per cubic centimeter, the bubble holds only a handful. With so little material to radiate excess energy, temperatures remain higher than the surrounding gas. This does not make the region safer, it makes it transparent. Energetic particles pass through with fewer obstacles, contributing to the cosmic ray background experienced throughout the solar system. Its edges tell the most interesting story. The compressed gas along the walls can reach densities that collapse under gravity. The Orion star-forming complex is a likely example. Gas piled up over millions of years, then fragmented into new stars. Some of those stars will eventually explode in turn, potentially carving new cavities or reshaping the existing one. What we observe is not a single event frozen in time, but a chain reaction of energy release and material reorganization. Spacecraft crossing the heliopause reveal the contrast between solar and galactic environments. Inside the heliosphere, charged particles from the Sun dominate. Beyond it, the bubble's plasma and interstellar radiation become more influential. The transition is gradual. Particle direction changes, magnetic fields realign, and detectors register higher cosmic ray intensity. There is no distinct border, only shifting balance between internal and external pressures. The bubble affects observation. Astronomers measuring distances must account for how little intervening gas alters light. Regions that would appear dim or obscured in a denser environment may seem clear here. Studies of dust and gas distribution require correction for this cavity, or they risk underestimating mass. Even stellar motion simulations incorporate the bubble to understand how nearby stars interact with the galaxy's tidal forces. On timescales familiar to humans, the bubble appears static. On cosmic timescales, it is temporary. Our solar system moves through the Milky Way, and eventually it will exit into denser gas. New stars will explode, other cavities will form. Our region is not special. It is one stage in an ongoing cycle of destruction and renewal that governs the galaxy. We live within evidence of past violence, not as threat, but as context. The local bubble shows that space around our Sun was shaped long before the planets existed. Every probe, telescope, and spacecraft travels through a landscape sculpted by stars that vanished millions of years before life began on Earth. The Milky Way is not a pinwheel frozen in space. Spiral arms are regions where matter slows and compresses, igniting waves of star formation. Stars orbit at different speeds, drifting through arms rather than orbiting with them. Our Sun resides in a quieter spur between major arms, insulated from the most violent nurseries. The galaxy is not a static shape. It is a river of stars flowing around gravity's center. Spiral arms exist because motion meets density. As stars and gas orbit the galactic center, their speeds change with distance. The inner regions rotate quickly, the outer regions more slowly. This differential motion creates areas where gas clouds bunch together, like vehicles entering a slow zone on a highway. Compressed gas cools enough to condense, and massive stars ignite. The arm is not a physical structure. It is a pattern in which matter repeatedly gathers, forms, stars, and disperses. These arms are transient on galactic timescales. A star born in a spiral region does not stay with it. Over tens or hundreds of millions of years, it drifts away, carrying its chemistry and momentum into calmer surroundings. The arms persist not because the same stars remain, but because new stars continue to form where gas is compressed. Spiral structure is the history of physics in motion, not a fixed blueprint. The Milky Way's largest arms, the Perseus, and Scutum Centaurus arms host dense star-forming complexes. They glow in infrared and radio wavelengths, where cold dust and molecular clouds absorb and re-emit light. Within them, gravity divides raw gas into smaller fragments, each becoming a stellar nursery. High-mass stars form quickly, burn hot, and die violently, their radiation sculpting nearby clouds. These stars seed regions with heavy elements, but they do not last long. Their deaths in supernovae create bubbles, pushing material outward and triggering new waves of collapse. Our Sun did not form in its current neighborhood. Over billions of years, it migrated inward and outward as the galaxy evolved. Today, it orbits within the Orion Spur, a smaller branch between major arms. This position shields us from the highest concentration of massive young stars. Fewer supernovae occur nearby, and molecular clouds are comparatively sparse. The calm is relative. Dust drifts, gas streams, and radiation permeates the region, but the forces are less intense than within the main arms. Galactic rotation does not obey simple expectations. Unlike planetary systems, the outer portions of the Milky Way do not slow sharply. Their stars orbit faster than Newtonian predictions based on visible matter. This discrepancy led to the concept of dark matter, unseen mass that exerts gravitational influence without radiating light. The spiral pattern persists because this invisible halo stabilizes the galaxy, preventing the arms from winding too tightly. Travel through an arm would not present a wall of stars. Space remains mostly empty. The density increases only slightly, but that small change is enough to alter the life cycle of gas clouds. Instruments detect these regions through their emission lines, especially hydrogen. Radio telescopes trace the 21-centimeter signal that marks cold atomic gas, revealing the arms as long arcs embedded in the disk. Optical images cannot show the structure clearly because dust absorbs starlight. Our own location inside the disk adds obscuration. We see the arms as fragments rather than a whole. Within the arms, clusters form. Their members share age and composition. Over time, these groups disperse, their stars drifting into the larger population. Some clusters survive long enough to orbit as coherent units. Most dissolve into the galactic field. The Milky Way's history is recorded in their chemical signatures. A star's ratios of iron, carbon, magnesium, or oxygen reveal where and when it formed, long after the nursery has faded. Viewed from outside, the Milky Way would not appear serene. It would resemble a rotating ecosystem, arms forming, stars aging, bubbles expanding, gravity pulling everything into motion. The symmetry is not decorative. It is the visible result of matter responding to rotation, pressure, and time. Spiral arms are not paths for stars to follow. They are the places where galaxies reorganize themselves and renew. Toward the core, stars accelerate. Their orbits trace invisible curves around Sagittarius A star, a black hole millions of times the Sun's mass. We know it exists not by seeing it, but by watching stars whip around an unseen mass. Dust cocoons this center, but infrared reveals its mechanics. This object does not devour the galaxy, it stabilizes it. Without such a gravitational anchor, the Milky Way would unspool. The inner galaxy is dense. Star counts per cubic light-year climb rapidly. Old giants share space with clusters of newborn stars still wrapped in gas. Interstellar dust absorbs visible light, hiding most of the core from optical telescopes. Instruments that operate in radio and infrared pierce the obscuration, revealing motion. Arcs of stars orbiting a point that emits energy in bursts rather than steady beams. Sagittarius A star is the focal point. The black hole is not observed directly, the heated gas around it is. Material spirals inward, compressing and accelerating until friction and magnetic fields raise it to extreme temperatures. These flares rise and fade irregularly, not because the black hole is volatile, but because infall occurs in fragments. Clouds and stray stars feed it sporadically, then activity settles again. The clearest evidence comes from orbits. Near the center, a group of stars, S stars, complete full arcing paths in decades. Their trajectories are mapped with sub-millisecond precision. They accelerate near periapsis, then swing outward again, obeying gravity so intense that no cluster of ordinary matter could account for it. More than 4 million solar masses compressed into a region smaller than our solar system is consistent only with a supermassive black hole. The black hole does not pull everything into itself. Most stars in the central bulge follow stable orbits and will continue to do so for billions of years. Matter must lose angular momentum to cross the event horizon, and very little does. The majority of gas near the core circulates in long-lived streams. The idea of a galaxy slowly collapsing into its center is inaccurate. The core is a regulating presence, not an active drain. Energy does escape, not through consumption but through interaction. When infalling matter heats, it emits X-rays. When magnetic fields twist, jets of particles accelerate outward. Evidence of these past events exists in large bubbles of plasma above and below the galactic plane. They are remnants, not ongoing eruptions, signatures of episodes when the central regions were busier than they are today. The bulge surrounding Sagittarius A star is a dynamic environment. Orbits overlap, and gravitational encounters are frequent. Some stars lose their outer layers. Others merge or are ejected at extreme velocities. Planetary systems here would rarely remain intact. Perturbations are constant. The core is not inhospitable in a dramatic sense. It is simply crowded, governed by mass and motion. This arrangement is not unusual. Most large galaxies host similar central black holes. Their masses correlate with the mass of their stellar bulges, implying long-term coupling between star formation and central gravity. Without a heavy anchor, galactic rotation curves would shift and spiral arms would wind too tightly or dissipate. The black hole provides stability by shaping the potential well that everything orbits within. We observe the center through complementary tools. Infrared surveys track stars. Radio arrays map gas and magnetic structures. X-ray instruments monitor flares from newly heated matter. Each wavelength reveals a different layer of the same environment. Together, they form a consistent picture, a compact mass governing the inner galaxy, not by consuming it, but by holding the system together. Sagittarius A star is not the heart of the Milky Way in a symbolic sense. It is a physical requirement. The galaxy's stars flow around it because gravity demands order, and this mass gives the system its center. The galaxy rotates too quickly for visible matter to hold it together. Dark matter forms a halo that binds stars, clusters, and gas. We detect it through motion, not light. Stellar streams bend around invisible scaffolding. Satellite galaxies trace its contour. Dark matter is not an idea, it is a measured necessity, the framework every star inhabits. The evidence begins with rotation. In a system governed only by visible mass, stars in the outer disk should orbit slowly, as planets do far from the Sun. Instead, their speeds remain almost constant with distance from the galactic center. This flat rotation curve violates Newtonian expectation unless something unseen adds mass. That extra mass must extend far beyond the luminous disk, forming a halo that envelopes the galaxy. The halo does not glow, scatter light, or emit radiation. It reveals itself only by the gravity it exerts. Gravitational lensing provides a second line of proof. Light from distant galaxies bends as it passes massive objects. When we observe background galaxies distorted around foreground clusters, the curvature exceeds what visible matter can supply. The mismatch is consistent and repeatable. Even when clusters collide, as in the Bullet cluster, gas slows and lags behind, while gravitational mass travels onward. The lensing shows the mass and the matter have separated, indicating that most mass is in a component that does not interact strongly with normal particles. Dark matter is not smooth. It forms substructure. Tidal streams of stars, remnants of disrupted dwarf galaxies, warp and kink as they cross regions of varying density. Their paths act like tracers, revealing hidden contours. Where simulations of galaxy formation include dark matter, star streams behave as observed. Where simulations exclude it, or treat matter as only baryonic gas and stars, disks fragment or collapse into shapes our telescopes never see. The halo does not end where starlight fades. It extends hundreds of thousands of light-years, overlapping with those of neighboring galaxies. Dwarf satellites orbiting the Milky Way move faster than their visible mass suggests. Their survival, remaining coherent despite tidal stress, requires a reservoir of unseen mass shielding them from disruption. Without it, these satellites would dissolve into the galactic disk. The composition of dark matter remains unknown. It is not ordinary atoms, nor does it form planets, dust, or gas. Laboratory experiments search for candidates that could interact weakly with normal matter, particles that pass through detectors unnoticed most of the time, but leave faint traces in rare collisions. So far, no detection has matched expectations. The absence of a confirmed particle does not undermine the measurements. It simply constrains possibilities. Dark matter's influence stretches back to the universe's earliest structures. After the Big Bang, radiation and matter were tightly coupled. Ordinary gas could not clump until the universe cooled enough to decouple photons. Dark matter, unaffected by radiation pressure, began collapsing early. These seeds became gravitational wells into which gas eventually fell, forming the first galaxies. Without that scaffolding, matter would disperse too uniformly to produce large-scale cosmic structure. Galactic stability depends on it. Spiral arms persist because the gravitational potential well is deep enough to keep stars moving coherently. In models without dark matter, arms wrap too tightly or disintegrate. Central black holes do not solve the problem. Their influence is local, confined to the innermost region. Only a halo surrounding the disk maintains the observed geometry at large scales. The halo is quiet, not because it is gentle, but because it barely interacts with anything except gravity. Stars and gas pass through it without resistance. Collisions do not generate heat or radiation. The halo's motion is inferred, not observed directly, from how orbits maintain shape and how galaxies cluster in webs stretching across millions of light-years. Dark matter, therefore, enters our story not as speculation, but as constraint. The universe behaves as though this mass exists. Galaxy rotation, gravitational lensing, cluster collisions, satellite survival, all point to the same conclusion. Whatever it is, it defines the space in which luminous matter arranges itself. Every star, including the Sun, moves within a geometry set by something unseen, silent, and dominant. At the edges, dwarf galaxies orbit like moons. Their trajectories expose the halo's shape. Some are devoured, leaving stellar streams like footprints in darkness. The halo extends farther than the luminous disk, sometimes hundreds of thousands of light-years. This is the true size of the Milky Way. Not the glowing arms we see, but the gravitational field that surrounds them. The halo is a sparse sphere of influence. It contains old stars, globular clusters, and dark matter that does not emit or reflect light. Unlike the disk, where stars follow orderly paths around the galactic center, objects in the halo move in tilted and elongated orbits. These motions reveal mass that extends far beyond the visible galaxy. The stars do not slow with distance. They maintain speeds that imply a hidden reservoir of gravity. Dwarf galaxies are the most useful probes. They are small systems, millions of stars held together by their own dark matter halos. Their orbits around the Milky Way unfold on billion-year periods, crossing the halo repeatedly. Each pass distorts them. Tidal forces stretch their stars into long, thin streams. These streams are not artistic arcs, they are measurements. Their geometry shows precisely how the halo bends space. The Sagittarius dwarf galaxy provides a case study. It has been pulled apart over multiple encounters. Instead of a compact object, it now exists mostly as ribbons of stars that wrap around the Milky Way. Other dwarfs, like the Hercules or Carina systems, show similar signs of strain. Their survivors are fragments, not failures, evidence of how galaxies grow by absorbing smaller neighbors. Globular clusters also orbit in the halo, though they differ from dwarfs. They are dense balls of ancient stars, some older than the Milky Way's disk itself. They lack dark matter and are bound by stellar mass alone. Many travel on inclined orbits, indicating that they were captured early, likely from smaller systems. Their chemistry contains the timeline of the galaxy. Iron-poor stars from primordial eras and slightly enriched populations formed later. Gas in the halo is faint but important. It forms a circumgalactic medium, hot, thin plasma spread across hundreds of thousands of light-years. Supernovae in the disk expel material outward. Some returns gradually, seeding new star-forming regions. This exchange prevents the galaxy from exhausting its fuel. The process is slow, but persistent, operating over millions of years instead of seasons or decades. The halo's scale defies intuition. The visible disk spans about 100,000 light-years. The halo can reach 2 or 3 times that diameter. Objects like the Large and Small Magellanic Clouds orbit within this domain. They move not around the spiral arms, but around the Milky Way's total mass. Their paths arc through deep gravitational wells, not the thin sheet of stars humans usually imagine. Dark matter dominates this region. Its distribution is not perfectly uniform. Simulations and observations suggest slight clumps, subhalos, moving within the larger halo. When dwarf galaxies pass near them, their orbits wobble and their streams bend. By examining these deviations, astronomers can map structures they cannot see. The halo becomes a tool for measurement, not a mystery to decorate. None of this is perceptible from Earth. The halo does not cast light, reflect sunlight, or create a visual boundary. It is known through motion. The way clusters resist tidal breakup, the way streams maintain coherence, the way satellites orbit where visible mass alone could not sustain them. Every star, including the Sun, moves inside this gravitational envelope. The Milky Way's edges are therefore not where starlight stops. They lie where gravity stops holding objects in long-term orbit. The halo defines that threshold. It is the unseen architecture of the galaxy, the space through which smaller systems travel, and the quiet record of how the Milky Way assembled itself over billions of years. Our galaxy shares a neighborhood with more than 50 companions. Each follows paths determined by collective gravity. The Milky Way and Andromeda dominate, but dwarfs weave between them like smaller vessels in the wake of 2 large ships. Their motions are not chaotic. They are the visible consequences of dark matter shaping space. The local group is not centered on a single galaxy. Its members orbit around their combined mass, forming a loose gravitational system about 10 million light-years across. The Milky Way and Andromeda account for most of that mass. But smaller galaxies, some barely brighter than star clusters, record the structure of the region. Their orbits and distortions reveal how matter is arranged, even when we cannot observe it directly. Each system is a tracer, moving through the geometry carved by the whole. Satellite galaxies cluster around both giants. The Milky Way hosts the Magellanic Clouds, irregular systems filled with gas and active star formation. Streams of hydrogen connect them to us, evidence of tidal interaction. The Large Magellanic Cloud shears its smaller sibling, and both are slowly losing material to our halo. Their stars form arcs that extend far from their visible disks. The process is not violent at human scale. It unfolds over millions of years, written into orbits rather than explosions. Around Andromeda, satellites form a wider, fainter collection. Some travel in planar structures, suggesting shared origin. Others appear scattered, the remnants of past mergers. Andromeda's mass draws them inward, but not uniformly. Dark matter creates a potential well that shapes their trajectories. When one satellite loses coherence, its stars stretch into streams curving through the galaxy's outskirts. These structures confirm that gravity does not act from a single point, but through distributed mass. The space between the giants is not empty. Filaments of dark matter likely connect the Milky Way and Andromeda, guiding the overall motion of the group. Their mutual attraction is measurable. Both galaxies are moving toward each other at hundreds of kilometers per second, Precise measurements from missions like Gaia show Andromeda's sideways velocity may reduce the likelihood of a simple head-on collision, but the long-term dynamics remain governed by shared mass. The interaction will be slow, not cinematic, shaped by gravity across billions of years. Beyond the two dominants, systems such as Triangulum serve as intermediaries. Triangulum is a full spiral galaxy, smaller than the Milky Way, yet large enough to influence its neighbors. It likely orbits Andromeda, though the path is complex. Its gas and star clusters show patterns of mild tidal distortion, signs that it feels the pull of something larger. These relationships are not random. They reflect an ongoing exchange of motion and energy throughout the local group. The faintest members are ultra-dwarf galaxies, some containing only a few thousand stars. Their survival would be impossible without dark matter. Their visible mass alone could not resist tidal disruption. Their persistence indicates that they sit within dense pockets of unseen matter, small halos nested inside the larger field. When they stray too close to a major galaxy, the protective halo thins, stars peel away, forming stellar streams that mark where gravity exceeded their cohesion. This family of galaxies evolved together. Some were born from the same primordial gas clouds. Others arrived later, captured during the group's assembly. Their present positions represent only one moment in an ongoing migration. Over cosmic time, mergers, dissolutions, and orbital reshaping transform the landscape. Yet the group remains bound, moving through the expanding universe as a coherent gravitational unit. From Earth, none of this motion is visible. Andromeda appears as a faint smear in dark skies, the Magellanic Clouds as ghostly patches in the southern hemisphere. Their true nature emerges through measurement, radial velocities, proper motions, and the slow drift of stars across decades of observation. Together, these data show a system held not by proximity, but by shared gravity. The local group is our environment on galactic scales. It is not a cluster of isolated islands, but a network of worlds traveling through space together, each revealing the shape of the unseen mass that binds them. The nearest major galaxy does not drift away, it approaches. For decades, astronomers assumed an inevitable collision, a future spiral merging into an elliptical giant. Gaia and Hubble now complicate that story. The galaxies possess sideways motion, and their satellite companions tug subtly on their trajectories. Some simulations predict a merger in billions of years. Others show a near miss or long orbital dance. The future is not a single line, it is a spectrum. Gravity writes in probabilities, not promises. Andromeda, also known as M31, is massive enough to challenge the Milky Way's shape and momentum. For most of the 20th century, astronomers measured only its radial motion, how fast it moves toward us along our line of sight. That velocity is substantial, on the order of hundreds of kilometers per second. Early calculations treated the encounter like two objects on converging tracks, but galaxies do not behave like rigid balls. They are rotating disks of stars, gas, dust, and dark matter, each surrounded by satellites and tidal debris. Sideways motion, proper motion, matters as much as approach speed. Hubble and later Gaia provided the missing component, lateral drift. Andromeda is not heading directly toward the Milky Way, it slides slightly across the sky. Even a modest sideways velocity, scaled across millions of light-years, can shift the eventual trajectory dramatically. Instead of a direct collision, models now explore a range of outcomes. Some show a slow spiral inward, others show orbital loops that stretch over billions of years before eventual coalescence. A few predict that the galaxies may graze each other, exchanging material but not immediately merging. Satellite galaxies add complexity. The Milky Way is accompanied by the Magellanic Clouds and dozens of dwarfs. Andromeda has its own retinue. These companions exert gravitational pulls of their own, altering the motion of their hosts as they orbit. When a dwarf galaxy passes close to Andromeda, its trajectory tugs on the larger system. The effect is subtle on human timescales, but cumulative over cosmic durations. Simulations must account not only for two major galaxies, but for dozens of interacting halos moving within a shared dark matter environment. The halos themselves may be touching already. Dark matter extends far beyond visible disks, reaching hundreds of thousands of light-years outward. When halos overlap, the galaxies feel each other long before their stars do. The interaction is not dramatic, it is diffusive. Their motions adjust gently as mass distributions respond to one another. The question is not whether influence exists, but how it evolves. If a merger eventually occurs, it will not resemble two shapes smashing together. Stars in each galaxy are separated by such huge distances that collisions between individual systems are unlikely. Instead, gravitational tides will scatter orbits, reshuffle clusters, and compress gas clouds. New stars might ignite in the regions where material is squeezed. Over time, the disk structures would fade into a large, smoother galaxy with few defined arms. But this process would unfold over billions of years, not in sudden collapse. A near-miss scenario is different. The galaxies could pass by, exchanging only their outermost material. Streams of stars would peel away, forming bridges and tails. Both galaxies might remain intact, but their shapes would distort. They would then drift apart, possibly bound in a slow orbital dance that repeats over long intervals. This outcome remains plausible because we do not yet know Andromeda's exact transverse velocity with absolute precision. The debate is therefore not about drama, but about measurement. Every new refinement of stellar motion narrows the range of models. Gaia's ongoing data releases map the trajectories of stars in our own galaxy, allowing better estimates of the Milky Way's mass and momentum. Meanwhile, deeper surveys track Andromeda's motion against distant quasars, reducing uncertainty millimeter by millimeter each year. The question of collision or near miss is not a prophecy. It is a calculation in progress, shaped by gravity acting across scales too large to perceive in a lifetime. Andromeda is not a threat or a destiny. It is a neighboring world in motion, responding to the same physical laws that guide every star around us. Between galaxies lies true emptiness. Temperatures approach absolute zero. Distances stretch into millions of light-years. Even at light speed, messages would take epochs. The cosmic microwave background, fossil radiation from the early universe, fills this void like cold fog. Intergalactic space is not nothing. It is the canvas on which everything else is painted. Beyond the reach of galactic halos, matter becomes sparse to the point of abstraction. A cubic meter may contain a handful of stray atoms. What fills the space instead is relic energy. Microwaves stretch thin by expansion. This background radiation is uniform across the sky, a remnant of when the universe was young and dense. It is not warm. At about 2.7 Kelvin, it simply marks the minimum thermal state that normal matter tends toward when stripped of sunlight, starlight, and shielding gas. Intergalactic space does not eliminate gravity. It simply dilutes it. Each galaxy exerts influence, but distance weakens its pull until the collective mass of many galaxies determines direction. A lone traveler crossing this region would not feel pressure or wind, only inertia. Motion continues unopposed, because there is nothing to slow it. Fragments of dust drift for billions of years without collision. A spacecraft's course becomes a line, altered only by the rare encounter with a cluster's distant pull. The medium is not uniform. Between galactic islands lie filaments, long strands of gas and dark matter that link clusters into cosmic webs. Their density is low, yet meaningful. Hydrogen clouds stretched over megaparsecs influence how galaxies assemble and migrate. When light from distant quasars passes through these filaments, it absorbs specific wavelengths, allowing astronomers to treat the void as a laboratory. The gaps in the spectrum are not imperfections, they are footprints of matter too faint to see. Radiation behaves differently here. Without magnetic fields or atmospheres to scatter particles, cosmic rays travel unhindered. Some originate from supernova remnants or jets around black holes. Others come from events so energetic that no known process easily explains them. A probe crossing intergalactic space would face bombardment from particles that can pass through meters of shielding. They do not arrive as storms or bursts, they arrive as statistics, doses accumulated over decades. Heat has nowhere to go. In vacuum, conduction is impossible and convection meaningless. A body can cool itself only by emitting infrared radiation. Large surfaces radiate better, small ones struggle. Even a spacecraft designed for deep space must orient its thermal panels carefully to shed energy. Electronics are less threatened by freezing than by overheating in darkness. Time feels different when nothing marks motion. In a galaxy, orbits provide rhythm. Stars rise and set. Spiral arms sweep by. Clusters drift across the sky. In intergalactic space, there are no markers. A traveler sees only points of light that change position too slowly to notice. The universe expands silently, stretching wavelengths as the metric of space itself grows. What was once ultraviolet becomes infrared. What was infrared becomes microwave. Even the cosmic background cools gradually as the expansion continues. Signals are swallowed by scale. A radio message sent from one galaxy to another may travel millions of years before reaching its destination. The sender and receiver might not coexist by the time communication arrives. Engineering solutions cannot change this. Physics sets the interval. Intergalactic space enforces patience that exceeds civilization, technology, and geology. Material floating here usually began somewhere else. Some of it was ejected by gravitational encounters, stars tossed outward by interactions with black holes. Other fragments were stripped from galaxies passing each other. A few interstellar objects, such as the visitor known as Oumuamua, carry traces of that history. But most wanderers never approach a star closely enough to be detected. They simply drift along trajectories older than any planetary system. Seen from a galaxy, intergalactic space seems empty because it carries no glow, yet every cluster, filament, and satellite moves through it. It defines the boundaries of gravitational families. It sets the time horizon for light and matter. It is not an absence. It is the medium against which structure becomes visible. Clusters collect hundreds or thousands of galaxies within vast halos of dark matter. Gas between them glows in X-rays at tens of millions of degrees. These structures should tear themselves apart, yet dark matter holds them in place. Galaxies here move like commuters in a dense city, fast, near, and constantly interacting. A cluster is not a loose gathering. It is a gravitational well so deep that entire galaxies behave like particles inside it. When matter collapsed on cosmic scales, dark matter clumped first, producing large halos. Gas followed, heating as it fell into these wells. The result is intracluster plasma, thin, ionized gas occupying the space between galaxies. Although sparse, it is hot enough to radiate strongly in X-rays. This emission is measurable, allowing astronomers to estimate the total mass of a cluster. The numbers never match visible matter alone. Something unseen dominates the balance. Galaxies within a cluster do not orbit calmly. Their motions are high velocity and three-dimensional. Some plunge through the center and swing outward again. Others travel along curved paths guided by the cluster's mass distribution. Encounters are frequent. When a galaxy passes through intracluster gas, its own gas is stripped away. The process is known as ram pressure stripping. Tails of material trail behind the galaxy, marking its trajectory. These tails do not form because of wind. They form because the galaxy is moving supersonically through a medium that resists it. Collisions between galaxies are also common, though collision rarely implies star-to-star impact. Gravitational tides distort their shapes, compress their gas, and trigger waves of new star formation. Spiral arms warp, cores merge, star clusters are flung outward. Some galaxies lose so much material that only faint remnants survive, drifting through the cluster as ultra-diffuse ghosts. They are evidence of repeated encounters, not failed formations. The cluster environment is not static. Gas cools slowly, sinking toward the center. When enough gas accumulates, it can feed a central galaxy or its supermassive black hole. Accretion ignites jets of high-energy particles that blast outward, redistributing heat. These jets inflate cavities in the intracluster medium, bubbles spanning tens of thousands of light-years. The cycle is self-regulating. Cooling draws matter inward. Feedback prevents the entire supply from collapsing at once. Dark matter defines the architecture. Without it, clusters would disperse. The speeds of member galaxies far exceed what visible mass could bind. Gravitational lensing, light bending around the cluster, confirms this. The distortion maps the mass, revealing halos larger than the galaxies themselves. In clusters like Abell 1689 or the Bullet cluster, lensing patterns track where mass resides even when the hot gas has shifted elsewhere. The separation demonstrates that gravity is controlled by dark matter, not ordinary plasma. Clusters form hierarchically. Smaller groups merge into larger ones, carrying their galaxies and dark halos with them. The process is slow and layered. Filaments of the cosmic web channel matter inward over billions of years, feeding clusters like rivers feed basins. Magnetic fields twist. The result is not chaos, but re-equilibration on a grand scale. Life, if it existed near such environments, would find little stability. Frequent gravitational encounters would reshuffle systems. Radiation from hot plasma and active nuclei would bathe galaxies in energy. Planetary material might survive at distance from stellar cores, but the broader context remains dynamic. The cluster is a factory of interaction, not a refuge. Seen from within, a cluster would not appear crowded. Stars would remain separated by light years. Galaxies would still look like distant smudges. The density becomes apparent only in aggregate, through measurement and motion. What binds everything is gravity extending across megaparsecs, anchored to halos that outweigh the luminous contents by factors of several. Galaxy clusters are the largest gravitationally bound structures in the universe. They are not knots of randomness, but the endpoints of cosmic assembly. Places where gravity gathers what expansion tries to stretch apart. The local group drifts toward denser regions of spacetime. These flows form a gravitational basin called Laniakea. Its boundaries are traced not by walls but by motion. Galaxies fall toward attractors, like rivers descending towards sea level. We exist on one slope of this cosmic watershed, carried slowly toward the Virgo cluster. Laniakea is not a cluster or a filament. It is a region defined by the direction galaxies move when left to gravity alone. Instead of drawing lines around the brightest structures, astronomers mapped thousands of galactic velocities. They measured how each galaxy's motion differed from the smooth expansion of the universe, then traced those motions backward. The result was a basin, a wide domain where flows converge toward a central gravitational influence. This basin spans more than 500 million light-years. Its edges are where motion changes direction. The key to recognizing Laniakea was abandoning static boundaries. Galaxy groups and clusters overlap, but their trajectories diverge. Some galaxies fall toward the Virgo cluster, a massive system at the heart of our basin. Others descend toward different attractors in neighboring regions like Perseus Pisces. Where the tendencies separate, the boundary forms. Nothing marks it physically. It exists only in velocity space, the same way a continental divide exists in hydrology. Slopes determine where water flows, not lines on a map. Our local group is a small tributary. The Milky Way, Andromeda, and dozens of dwarfs move together, but they are part of a larger trend. Their motion is not random. It is biased toward Virgo. The Virgo cluster is massive enough to bend the trajectories of thousands of galaxies, even across tens of millions of light-years. Its gravity does not overpower the expansion of the universe, but it modifies local movement. That modification is what defines the basin. At the basin's center lies the Norma cluster, also called the Great Attractor region, a dense knot of mass buried behind the Milky Way's dust. Its presence was inferred long before it was visualized. Astronomers noticed that galaxy catalogues showed an asymmetry in motion. Systems toward one direction appeared to be pulled forward. Optical surveys were blind to the culprit because the galactic plane blocked the view. Infrared and radio work eventually revealed clusters, filaments, and dark matter concentrations large enough to explain the phenomenon. Flows within Laniakea resemble currents in slow motion. Galaxies do not plunge, they drift. Every system retains its own orbit around its local group or cluster, but superimposed on these motions is a gradual descent. It is not felt as force, only observed in aggregate. The Milky Way will never notice the flow within a human lifetime. The distance measured from year to year is smaller than a grain of sand compared to an ocean. Yet over billions of years, the trend becomes clear. Motion aligns with gravity. Laniakea does not imply stability. The basin itself is part of a larger cosmic web. Beyond it lie other basins, each with their own attractors and directions. The universe on these scales is not a chaos of galaxies, but a vast network of gravitational gradients. Where matter is densest, galaxies gather. Where it is sparse, voids expand. Boundaries are porous. Clusters exchange material. Filaments stretch and loosen. The basin model captures behavior, not permanence. The picture remains incomplete. Measurements require knowing true velocities, not just how galaxies appear to move. Distances must be calibrated precisely, and uncertainties compound over millions of light years. Laniakea is the best reconstruction available, not the final one. Future surveys may redraw its outline, identify deeper anchors, or reveal that its flows belong to an even larger basin. Whether its edges shift or hold, the idea endures. We are not isolated. The Milky Way is part of a pattern of motion extending across hundreds of millions of light years. We fall, slowly and silently, down a slope carved not by terrain, but by mass. Between superclusters lie enormous cavities. Matter here is scarce, gravity weak, and expansion dominant. Galaxies near their edges accelerate outward, drawn toward denser regions. Light passing through voids appears cooler, its energy stretched by the lack of gravitational wells. These are not errors. Voids occupy most of cosmic volume. Density exists in islands. A supervoid is not a hole carved out of space. It is a region that simply never collected enough mass to form complex structure. In the early universe, slight variations in density determined where matter would collapse. Where fluctuations were large, halos formed, gas cooled, and galaxies assembled. Where fluctuations were small, expansion pulled material apart faster than gravity could gather it. The result is absence by evolution, not removal by force. Voids are the untouched residue of initial conditions. Scale here is difficult to internalize. A void can span hundreds of millions of light years, yet its boundaries are soft. Dwarf galaxies, filaments, and isolated groups sprinkle its interior like embers in a cold furnace. These outliers do not contradict the emptiness. They illustrate it. Their orbits reveal minimal gravitational influence. Their gas reservoirs remain vulnerable to tides from distant clusters. They survive only because the surrounding environment is too diffuse to disrupt them. The temperature of light passing through a void changes subtly. Cosmic microwave background photons lose energy in regions where gravity is weak and expansion dominates. This effect, known as the integrated Sachs-Wolf phenomenon, does not produce dramatic signatures. It produces faint cooling, microwave shadows stretching across the sky. When mapped statistically, these shadows align with the locations of large voids, confirming their influence on radiation traveling from the early universe to the present. Galaxies near a void's edge behave differently than those embedded deep within it. At the boundaries, mass is denser. Filaments connect to clusters and superclusters, forming gravitational slopes. Systems on those slopes accelerate toward denser regions, not because something pushes them, but because the void behind exerts little counterweight. In cosmological simulations, filaments tighten around these margins like vascular networks, channeling matter inward. The void expands slowly as its edges migrate outward. The interior evolves passively. Gas is too sparse to collapse efficiently, and there is little external shock to compress it. Star formation slows. Existing galaxies age quietly, forming small populations of older stars. Their halos stretch, but their growth stalls. They are not deserts in a dramatic sense. They are regions where the mechanisms that build structure rarely activate. The stillness is not absolute, it is statistical. Supervoids do not isolate the universe into compartments. They provide contrast. They reveal where gravity has succeeded and where expansion has prevailed. The cosmic web, the network of filaments, nodes, and clusters, exists because matter chose direction early, inward toward basins or outward into emptiness. Every map of large-scale structure shows the same pattern. Dense threads separated by wide, dark expanses. From a spacecraft crossing such a region, the sky would not appear different. Stars would still fill every direction. Galaxies would remain faint smudges. The void becomes visible only through measurement. Redshift surveys, gravitational lensing, microwave background patterns. Even then, it appears as subtraction, places where signals thin, not where something stands out. Its significance lies in its lack of features. Voids expand in step with cosmic growth. As the universe stretches, low-density regions widen faster than dense ones, because gravity in clusters resists expansion. Over billions of years, islands of matter drift farther apart, and the oceans of empty space deepen. This trend does not imply final isolation, only that large-scale structure becomes more pronounced. Clusters grow denser, voids grow larger, and the contrast between them sharpens. Supervoids are reminders that the universe is not built uniformly. Most of space contains almost nothing, yet that emptiness defines where everything else forms. Galaxies, clusters, and superclusters are statistical peaks scattered across a landscape dominated by scarcity. We live on one of those peaks, surrounded not by walls, but by distances so great that gravitational influence fades into quiet. Zoom far enough out, and the universe reveals itself. Filaments of matter connect clusters across hundreds of millions of light-years. Voids sit between them like bubbles between walls. Galaxies are beads in these filaments, following paths written in the earliest fluctuations of the Big Bang. The web is not decoration, it is the largest architecture nature has built. The cosmic web emerges from gravity, acting on slight variations in density after the universe cooled. Where a region contained a little more mass than average, gravity amplified it. Gas collected, then dark matter. Those regions became gravitational wells. Between them, lower density areas continued to expand, stretching into voids. Over time, these boundaries sharpened until the universe resembled a foam of cavities and filaments. The pattern is not imposed, it is the outcome of physics applied across billions of years. Galaxies do not form everywhere. They form along the web's strands, where gas condensations grow dense enough to ignite star formation. Clusters appear at intersections, nodes where filaments converge and mass accumulates. They are the metropolitan centers of cosmic structure, drawing in smaller systems from surrounding filaments. The web, in this sense, is not a map of static lines but a network of flows. Matter continuously streams toward deeper wells. Simulations reproduce this pattern. When cosmological models include dark matter and expansion, filaments emerge naturally. When dark matter is removed, the structure collapses into unrealistic shapes. The match between observation and simulation is striking. Radio surveys trace hydrogen clouds across tens of millions of light-years, revealing filaments almost exactly as models predict. The agreement is not aesthetic, it validates the underlying physics. Light interacts with this structure. When photons from distant galaxies travel through a filament, gravity bends their path slightly, distorting the shapes we observe. These distortions, weak lensing, map the web's skeleton. The densest regions produce stronger bending. Sparse regions barely touch the light. By combining millions of such measurements, astronomers reconstruct a three-dimensional view of mass distribution, independent of brightness. The brightest galaxies trace the architecture, but the lensing shows the deeper framework they sit upon. Galaxies migrate along filaments as they evolve. Groups of systems fall toward nodes, merging with larger clusters. Cold gas flows inward like fuel lines, feeding star formation in central galaxies. Sometimes, this gas is stripped or heated by feedback from black holes or supernovae, altering how stars form along the strand. The web is not passive, it continually redistributes matter and energy. Its evolution shapes the histories of galaxies, not the other way around. In voids, the opposite occurs. Without strong gravitational wells, matter thins. Star formation slows or halts. Isolated dwarf galaxies drift, survivors of inefficiency. Their gas remains uncompressed. Their orbits reflect little more than the broad expansion of space. The contrast between void and filament is not cosmetic. It defines which areas of the universe become active and which remain quiet. The web spans scales beyond local comprehension. A single filament can run 300 million light-years. A supercluster, anchored to its intersection, may contain thousands of galaxies, each with their own satellites. Yet most of the universe between these strands is empty. What looks like a connected lattice is mostly gaps, regions where gravity lost its competition with expansion early on. Humans see none of this directly. Through a telescope, the sky is scattered with points and smudges. Only when maps are stacked, distances measured, and motions plotted does the pattern emerge. The web is not a single observation. It is the accumulation of millions of measurements, each showing matter obeying the same rules across immense scales. The cosmic web is not a structure we can travel across. It is the environment from which every galaxy arises. It shows that the universe is not random. It organizes itself through gravity, temperature, and time. Filaments tell us where matter goes. We inhabit one strand among many, part of an architecture so large that galaxies become components, not endpoints. In a network formed by the earliest ripples of creation, the journey outward always returns to us. We left Earth as a body of air and oceans, crossed the exosphere, navigated orbital lanes, walked on the moon, drifted past gas giants, and stepped beyond the Kuiper belt into the long tail of our star's influence. We moved through the heliopause into interstellar space, traced the scars left by ancient explosions, and crossed into the quiet regions between suns. We learned that the Milky Way is not a single wheel of stars, but a network of arms braided by gravity, stabilized by a black hole we cannot see. We found that most of its mass is invisible, yet measurable in every orbit. We witnessed how the galaxy is only one member of a family, shaped by Andromeda's motion and the pull of satellites still forming their own paths. Farther out, the pattern changed scale. The local group became a tributary flowing into Laniakea's basin. Galaxy clusters collected like cities at crossroads. Voids opened where structure never formed. The cosmic web stretched across hundreds of millions of light-years, threading gravity into filaments more durable than any single galaxy. Everywhere, the same principle held: matter follows motion, and motion follows mass. There is no grand hierarchy, only energy and time. Nothing in this journey diminished our place. It clarified it. Humanity is not central, but neither is it trivial. We are a product of calm regions, formed in a spiral spur, protected by a magnetosphere, stabilized by a moon, and gifted molecules synthesized in stars that burned before our sun existed. We are the universe examining itself through instruments, mapping flows and voids, not because we seek dominance, but because curiosity is the only way we understand our environment. Some questions are still raw edges. We do not know the particle nature of dark matter, or whether Andromeda will embrace or sidestep us. We cannot see the Oort cloud directly or resolve the deepest filaments without inference. The web may hide structures we have not yet imagined. These are not failures, they are the frontier. Every unanswered question is an invitation to return, refine, and see again with clearer tools. When we look outward, we glimpse history written in motion. When we look inward, we see the conditions that allow us to ask the questions at all. The universe is not waiting for us to understand it. It simply continues, expanding, cooling, clustering, dispersing. Our task is to observe honestly and to recognize that discovery is a process, not a destination. The galaxies will keep drifting, the stars will keep forming, and somewhere, generations beyond us will draw new maps, correcting ours with the same confidence we apply today. The story does not end with the edge of the observable universe. It ends only where curiosity stops. Here, standing beneath a sky that is no longer simple or small, we take our place not as spectators, but as explorers who know that the journey forward is always open. But for now, rest and sleep well. Good night.